All right, guys, so we're going to go ahead and start in on Unit 3. This piggybacks off of Unit 2. We're still looking at the atom itself and its structure, but we're going to look at the more advanced models of the atom, or the more modern ones. So going beyond just how many protons, electrons, and neutrons there are, looking at how these are going to be arranged in the atom itself. As always, the very first slide has some important vocab on it, so I would make sure to kind of highlight these as we go through. These are ones that may come up from time to time. So this unit, we're going to start off talking about the Bohr model of the atom. So this one is what really kind of sparked all of our advancements in our atomic knowledge. So Bohr adapted Rutherford's model to include discoveries of how the energy in an atom changes when it absorbs or emits light. So Rutherford's model just had the protons and neutrons kind of floating around, or excuse me, the protons and neutrons in the nucleus of the atom. And then the electrons were just kind of floating around. They didn't really have an idea of where those electrons were located. So Bohr adapted this to look and focus more on those electrons and looking at where those were, and looking at whenever a substance has electricity or energy, it gives off light, and looking at kind of how or why that happens. So Bohr proposed that an electron is found only in circular paths or orbits around the nucleus. So he said that the nucleus has those protons and neutrons, but that you had these circular paths where all of our electrons are going to be found. And he said they could only be on those circular paths. So that's something that was different. He said that the electrons have to be in these paths, orbiting similar like planets orbiting the sun. He said that these different pathways, these different circles around the nucleus, are energy levels. These are fixed energies an electron can have. So electrons have to be on these levels. They can't float in between levels. So he said these energy levels are similar to rungs on a ladder, where, like, if you're climbing a ladder, you're not going to levitate between two rungs of a ladder. You're either on one or on the next one up. He said that the lowest rung, the one closest to the nucleus, has the lowest energy, and you can go up or down levels by gaining or losing energy. And yet again, you cannot be between energy levels. So electrons are going to be in the lowest energy level possible, so the one right outside the nucleus. And if they gain energy, they can jump up from one level to the next. And if they lose energy, they can fall down back to that lowest energy level closest to the nucleus, which is our ground state, is going to be that lowest energy. All right, so he said that difference between those orbits that he had, between those energy levels, is a quantum. A quantum is the amount of energy required to move an electron from one energy level to another energy level. And this is just a set amount of energy. So we say that energy is quantized. It's a certain amount. And this, I'm going to try to draw it, but you can see this if you look on your reference sheet. The very back page has a Bohr diagram where you have the nucleus in the center, and then you have these energy levels. Oops, excuse me, I can't draw circles. All right, so this amount of energy is not the same going from every single energy level. So if you notice, from this first energy level to the second energy level, that is a pretty big gap. So the closer to the nucleus the electron is, the more energy it will have to gain to jump up a level. So this is a larger gap an electron will have to gain, versus if it's going between the second and the third energy level. That is a much smaller value So it doesn't need as much energy to jump from that second level to the third level. And you'll notice on your reference sheet, the further away you go from the nucleus, those energy levels get closer together. So it doesn't take as much energy to jump a level. And like we said, that energy can be gained to jump up levels. That energy can also be lost, causing the electron to fall down a level. And whenever an electron falls from a higher level to a lower level, it gives off light energy in the form of a photon. So this is part of what we're going to be looking at with the Bohr diagram, is looking at the light that is given off from it. And Bohr's model really only works for hydrogen, which is why it is not our current model, but it was noting the behavior that we saw from one of the different atoms. All right, so just to kind of show you what this looks like, according to Bohr's model, the protons and neutrons are in the nucleus, and then the electrons are on those specific orbits. Now notice that this is drawn pretty two-dimensional. This is imagined as a three-dimensional substance, where those rings don't necessarily line up in the same plane, and it is a more three-dimensional structure. This picture up at the top is similar to what you see on your reference sheet, where you have the nucleus in the center, that red dot. The blue line is that first energy level. That's that ground state. And then you have all the other energy levels. This just tells you the actual energy amount, the value of the energy for each of the energy levels. So notice that the n equals 1 is that ground state. From 1 to 2 is a jump of about 10.2 volts of energy that they're measuring. So that electron would need to gain 10.2 volts of energy in order to jump from level 1 to level 2. But going from level 2 to level 3 is less than 2, or slightly more than 2. So that's a much smaller jump. Going from level 3 to level 4 is only about a 0.7 difference. And that gap will get smaller and smaller as we move away from the nucleus. So with Bohr, all of his studies were based off of a substance giving off light. The study of light is what led to the development of our quantum mechanical theory and Schrodinger's equation, which the quantum mechanical model is our current model of the atom. And this was by looking at the behavior of light. So Isaac Newton in the 1700s was the first one to kind of theorize that light consisted of particles. Particles, this deals a little bit into the physics part of chemistry, but particles tend to move in a straight line until they are acted upon by something else. They will move in a straight line until they bounce off another object. But particles tend to not move around objects. They move in a straight line and then bounce off. Whereas we were noting behavior where we can end up with shadows, where light does go around objects. It's just more dim. So in the 1900s, they decided that light might consist more of waves, where it can actually move around objects versus moving in a straight pathway. So looking at these behaviors helped us develop these more modern models of the atom. So with light behaving as a wave, looking at what's happening. So here we have a picture of a wave. You may remember waves back from earth science, but it's been a while. But with waves, it does kind of go up and down the same amount. So amplitude is the wave height. So from that baseline, which is kind of a pink color for us, it's from the baseline to the top, the crest of a wave, or from the baseline down to the trough of a wave. This should be the same amount. And the amplitude is going to deal with the brightness overall. So if you have like a really bright LED light, that might have a higher amplitude than like a soft white light bulb in a lamp. Wavelength is going to be the distance between identical parts of waves. So here it's depicted as going between two crests that are identical. That distance is our wavelength, and that's represented as a lowercase lambda, which you can see in the picture. And that should be the same between any two parts of the wave. So if we measured between the two troughs, that wavelength would be the same. With waves, we also look at frequency. This is the number of wave cycles to pass a point in a certain amount of time. So if we were sitting still and counting the number of waves that pass us in a minute or something like that, that would be the frequency. And frequency is measured in hertz for us. We are not going to have to calculate wavelength and frequency, but we'll look at knowing what things have a larger frequency versus a larger wavelength and how these are compared. So with waves, all waves are a different type of electromagnetic radiation. This includes radio waves, microwaves, infrared waves, visible light, ultraviolet waves, X-rays, and gamma rays. And yet again, if you look at the back page of your reference sheet, down at the bottom in the right corner, you have an electromagnetic spectrum that shows all these different types of waves in that spectrum. All types of electromagnetic radiation travel at 3.0 times 10 to the 8th meters per second. That is the speed of light. And you'll see this represented as a lowercase c in equations. And all of our radiation, because they travel at the same speed, what makes them different types of radiation are their wavelengths and frequencies. So radiation is a range of frequencies and wavelengths in the spectrum. So the frequency and the wavelength is how we can tell what type of radiation we're dealing with. How these kind of relate to one another. And you, yet again, don't have to calculate this. I just wanted to show you how these compare. So the c, the speed of light, is equal to its lambda times nu, its wavelength times frequency. So whenever you have two factors that are being multiplied together, they are what we refer to as inversely proportional. So frequency and wavelength are inversely proportional. That means if one of them goes up, the other factor is going to go down. So if we have a really long wavelength, we have a low frequency. If we have a short wavelength, we have a very high frequency. And you can kind of see this. Most of this is invisible to the naked eye. But like whenever sunlight goes through a prism, you're going to get it where it splits into that rainbow, and the different frequencies split into the spectrum of colors or the rainbow due to longer or shorter wavelengths. So that's why a rainbow always has like the red on top and the violet on the bottom, because red light has a longer wavelength, so it can't bend as much, whereas violet light is a shorter wavelength, so it can bend a lot. So that's what gives us that different gradient of colors, are the differences in wavelengths and frequencies. But like I said, you're not going to have to calculate this. You do need to know that the two things are inverse. So if one is high, the other is low, and be able to get information from your reference sheet, looking at that electromagnetic spectrum to answer questions. So we'll look at that in a moment. So here's what is on that last page of your reference sheet. You have the Bohr model up top, and then you have the electromagnetic spectrum on the bottom. And I'm gonna see if it'll let me move this up slightly. So I'm gonna have to scroll down. We can't get the whole thing in here. But here it does give you Bohr's model for hydrogen. So it notes the nucleus in the center, and then those energy levels are the n equals 1, 2, 3, 4, 5, 6. Here it shows you electron transitions. So it shows you like a dot is where an electron would be starting, and then an arrow depicting where the electron would fall to. That gives you an associated wavelength measured in nanometers for whatever that electron transition is. So this tells us what type of energy is given off, or what type of light is given off in that circumstance. And yet again, you have that electromagnetic spectrum at the bottom. And here it does have wavelengths, but they are measured in meters instead of nanometers. What you're going to have to be able to do with this part of your reference sheet is you're going to have to be able to read a Bohr diagram or interpret Bohr diagram questions. So like I said, each of these lines is an electron transition. So this line over to the far right is saying that we're starting at n equals 4. Oh, excuse me, my pen fell asleep. We're starting at n equals 4 and going down to n equals 1. And it tells us that gives off 97 nanometers of wavelength. Is that energy that's given off has a wavelength of 97. That would correspond to a type of UV light because it's a shorter wavelength. What we're going to be focused on is this section of visible light that's in the middle. These are the electron transitions we need to be able to know and recognize. And let me scroll up real quick. All right. Oops, excuse me. Okay. So like I said, we are looking at that middle part of visible light. You need to be able to recognize what electron transition is going on at each of these points and be able to figure out what color of light that is going to give off. So this coincides with your electromagnetic spectrum down below. So our first line to the right in that visible spectrum is this one that it goes from n equals 6 down to n equals 2. And notice that it is going down. So you're only going to see light whenever it drops levels. So it goes from a higher level to a low level. That tells us that it is 410 nanometers is the wavelength given off. Well, down at our electromagnetic spectrum at the bottom, all of those measurements are in meters, not nanometers. So how this changes into meters is this will become 4.10 times 10 to the negative 7th. That's using those metric conversions we learned in Unit 1. You don't have to convert it every single time. Just understand that it's now going to become a decimal number. So that decimal number, if you look at our spectrum down below of visible light, the part that is kind of split down at the bottom, 4.10 is going to fall between 4.0 and 4.2. So this will end up being violet light. That one transition will produce violet light. We can do the same thing for the other 3 lines that are in the visible light spectrum. So looking at the next line, it is going from n equals 5 to n equals 2. That gives off 434 nanometers, which is going to translate to 4.34 times 10 to the negative 7th meters. So 4.34 is going to fall between 4.2 and 4.9. So this will end up being blue light for that electron transition. For our next one, This is the line that it goes from n equals 4 to n equals 2. It produces 486 nanometers wavelength. That is going to translate into 4.86 times 10 to the negative 7th meters. That also falls between 4.2 and 4.9. So this will also be blue. And then that last electron transition that is in that visible light spectrum is the n equals 3 to n equals 2. That is a wavelength of 656 nanometers, which will become 6.56 times 10 to the negative 7th. 6.56 falls between 6.5 and 7.0. So that will be red light. So what that actually shows us is it shows us the emission spectra for this hydrogen. So it shows us which specific wavelengths or bands of light will be given off. So with the emission spectra, whenever we look at hydrogen that is being electricity run through it or heat run through it, it will split up and it will produce a band of red light, 2 bands of blue light, and I don't have a violet option, so I'm going to use green instead of violet. And then that should be violet. So it only gives off a set wavelength of light due to the energy differences for hydrogen. So you're only going to have to be able to read this diagram for hydrogen. But like I said, you're looking at the electron transition or the wavelength that is given off or the color of light. So this is kind of all the possibilities of things you will be asked to find from a Bohr diagram. And remember that this energy is only given off whenever it goes from high to low. Whereas if we had electron transition and it went from 2 to 6, we are going to see nothing, because light is only given off whenever it goes from high to low. If it goes from low to high, it is absorbing energy and we don't see anything. All right, so real quick, I just wanted to show you a sample of the emission spectra. This is what we just found with hydrogen. So if you notice that second line of hydrogen, it has a red stripe, 2 blue stripes, and a purple stripe. That is the emission spectra for hydrogen. If you get a chance with one of the other teachers, they'll let you look at the spectral tubes. This is going to be a different spectra whenever you're dealing with different elements. So like helium, which only has 1 additional electron. Whenever you run electricity through helium, you're going to see multiple yellow or multiple red lines. You're going to see yellow, several blue lines, and some violet. So even just having 1 additional electron, you're going to see a variety of colors overall. Or for example, oxygen, you're going to have red lines, some orange, yellow, blue, and violet. So this you could use to match up like an unknown gas. We don't have to go that far with these. It's just understanding that whenever electricity runs through a substance, those electrons get energized and they jump up levels, and then eventually they can't stay up there forever. They lose energy and they fall down, giving off these certain wavelengths of light. So that was from Bohr's model of the atom. That led us to a more modern model of the atom, which is the electron cloud model. So scientists kind of disproved Bohr's theory looking at the different energies because it didn't work for anything other than hydrogen. So they didn't really believe that the electrons orbited the nucleus like planets. So they thought that electrons were more unpredictable, and we couldn't necessarily tell where electrons were at any point in time. So this led us to our electron cloud model. This is a more visual model of the atom that shows you where you're likely to find electrons at any point in time, but they can be other places. Whereas with Bohr's model, the electrons had to be in those energy levels and they couldn't be anywhere else. So this cloud is going to be most dense, where you're more likely to find electrons. And scientists use the electron cloud model to describe the possible locations of electrons around the nucleus. Like I said, where they're likely to be, but they can be other places. So here's what the electron cloud model looks like. And here's just two depictions of it. So the picture on the left, notice we have the nucleus in the middle. There's a band of electrons right outside the nucleus that's very dense. And then further out, there's a darker band going out from the nucleus as well. Where those bands are most dark is where you're most likely to find electrons. But notice between the two dark bands, there's still dots. There's still locations where the electrons can be. It's just not as likely to be between those two bands. You can see this as well in the picture on the right. This shows you the nucleus in the center. That darker orange band right outside the nucleus holds electrons. And then there's a band further away that is a darker orange. So electrons are most likely to be in one of those bands, but notice between, it is still a pale orange color. Electrons can still be between those. It is just not as likely. This is going to lead us into our quantum mechanical model, which is our current model of the atom that we will talk about tomorrow.